Hey folks, it's Mr. Byros. We're going to do a problem with a system of objects that are all connected by a string. So here we have three masses, little m1, little m2, and big M. So all three of them are connected together by a rope or a string, and we are going to figure out a couple things about them. So m1 and m2 are both sitting on top of a table. We have friction on the table. The coefficients of friction for the table are μs and μk, 0.5 and 0.43 respectively. Our big M, 12 kilograms, is hanging off the edge of the table, connected to the other two, and we'll assume no friction on this pulley that's connecting them. Now, what the problem asks us to do is find the total acceleration of our three block or three object system. So we need to find a total. We also need to find the force of tension experienced by mass M1. So we'll start by finding the total acceleration for the system. Now, in order to do that, we have to consider all three of these blocks together and their mass together as one system or one thing. Then we have to consider the external forces that are acting on that. So in order to do that, we'll set up a free body diagram, considering our body for the free body diagram to be all three of them combined. So I'm going to do that over here. I'm going to take this box will represent our three object system. Now we know that there's gravity. So there's gravity acting on our system. There's a couple ways we can represent this. So there's gravity acting downwards on blocks M1 and M2. But we know that gravity is going to be balanced out by the normal force. So in the y direction, we could draw a couple things. We could draw force of gravity for M1 plus M2. And we could draw the normal force for M1 and M2. Those two are going to be equal and opposite. They're going to be balanced. Those forces are going to be exactly the same. And we can figure out how big that is. The combined mass of M1 and M2, that's just equal to 7 kilograms. And of course, the acceleration of gravity is 9.8 meters per second squared. So I'm going to run that math real quick here. 7 times 9.8. So 68.6 newtons will be the combined force of gravity for M1 and M2. And it's also equal to the normal force for those combined objects. Now, in the vertical XY directions, we also have a couple other things that we're dealing with. One of those is the force of gravity on our big M. So I'm going to draw that as well on here. So in addition, we have force of gravity on block big M. Maybe should have left more room. I'm going to do the solving down here for that one. So Fg for big M is equal to 12 kilograms times 9.8 meters per second squared. Let's figure out what that is here. Times 9.8 gets us 117.6. So I should probably make this a little bigger. At least make it bigger than my other force of gravity and normal force. Alright, so there's the force of gravity for block big M. So that was equal to 117.6 newtons. Here, Fg big M is 117.6. And if we look at our three block system, that should be the only external forces that are acting in the x and y direction. Now you might say, what about tension in this rope? Isn't tension pulling upwards in the y direction, so shouldn't we include that on our free body diagram? Now this is where we have to be careful for our multi-object system. The force of tension between any of these blocks, the force of tension felt in those ropes, is an internal force within that three block system. So we don't include it on this free body diagram, which, as I remind you, is M plus M1 plus M2. This is all three of our objects together. Gravity is an external force acting on them. pulling all of them down. Here's the force of gravity pulling M1 and M2 down, force of gravity pulling big M down. Also, we have a normal force. Normal force is external. It's from the table pushing upwards on blocks M1 and M2. But for our 3-block system, gravity Fg for M1 and M2 and normal force are just balancing each other out. So they're not affecting the motion of the system in any way. All right. That should be all our y direction forces because we don't have to include tension here because tension is an internal force. We'll do that once we do the second part, finding the force of tension on M1. So sticking for finding a total, we should also do our x direction forces. So the only x direction forces that are pulling on this system is the force of friction. And actually, this brings up a very interesting point now. We can no longer describe this solely in terms of x and y directions because our direction of motion, our system is going to accelerate either this way, where block big M goes down and the other two go across the table to the right, or it could possibly accelerate this way. Now, we know that because there's friction and no applied force, either it's just going to sit still or the object is going to accelerate down this way. So we can't possibly have an acceleration. It's not going to accelerate this way. It can only accelerate back this way. So we have to describe this in terms of, we're going to call this a positive acceleration or a positive direction, and we're going to call this a negative. So I'm also going to have to slightly edit my free body diagram. So one way that I could change this, on the free body diagram, if I'm trying to describe this as all the objects together, one way I could do this is to rewrite Fg big M. Instead of putting it here, I can leave these here. They're not relevant to motion in these directions. They're only in this direction. So instead of the x direction, I'm going to call this, I'm going to just say this is my direction of positive motion. So anything that's moving or accelerating this way, where block M goes down and these two go to the right, is positive, and the other will be negative motion. Now instead of the x direction here, I'm actually going to put Fgm right here. So Fg big M, the force of gravity on this block, an external force to this system, is attempting to accelerate the system in the direction of positive motion. So Fgm is a force that is acting in the direction of positive motion, as we have defined it here. It does get tricky trying to figure this out, but we have to define this because we can no longer just talk about y and x as we stated before, because our y direction forces here are affecting the x direction motion of these objects, and we want to consider them together. So because we want to put them together, we're going to talk about positive motion, positive direction motion, and negative direction motion. Now the force that's acting back the other way is of course a friendly force of friction. Now we don't know yet if it's static, if it's kinetic, if the objects are moving, if they're not, so we'll have to figure that out, but we know friction is opposing this motion. All right, I think that should be everything. Again, tension is an internal force, so we don't have to worry about that. But what let's do, let's first look at the force of static friction, and let's see if Fgm is strong enough to overcome that and have our objects move, because we just need to double check that. We know that the coefficient of static friction is 0.5. We know our force of static friction will always be somewhere less than or equal to a maximum value, 0.5 times our normal force. Now we need to define what normal force that is. Objects M1 and M2 are both in contact with the table. So the normal force we're talking about is this combined normal force for M1 and M2, because the force of static friction will affect both M1 and M2 as they're sitting on the table. So this is normal force for M1 plus M2. So the force of static friction is less than or equal to 0.5 times 68.6 newtons, or less than or equal to 34.3 newtons. So the maximum possible value for the force of static friction is 34.3 newtons, much less than the force of gravity for big M. Therefore, this force is not going to possibly be strong enough to stop the objects from accelerating in the direction of positive motion. So we know that we have drawn it correctly. It looks like FGM is going to be bigger than the force, and we now know this is a force of kinetic friction because our objects are going to accelerate. Our system is going to move in the direction of positive motion. As we do that, we're going to draw a equation. Let's put our equation for Newton's second law, because what we need to do to find the acceleration is sum of forces, and we'll say that this is the sum of forces in the direction of motion. So again, this is our positive negative motion. We can no longer use sum of forces x, sum of forces y, because we have a system that can move in the positive or negative direction, but we're not limiting it to x and y. So sum of these forces, again, this is our FGM and our force of kinetic friction. So FGM is pulling in the direction of positive motion, and force of kinetic friction is pulling in the negative direction when it comes to that. So our direction of negative motion will subtract force of kinetic friction, and that's the sum of forces on our object, which should be equal to the mass of our object times acceleration, the total acceleration of our three-object system. Now, speaking of our three-object system, let's take a look at this mass. Because we're treating all of them as together, combined, we need to make sure this mass accurately represents that. So this needs to be big M plus M1 plus M2, because the acceleration of the total acceleration of our system is going to depend on the mass of all the objects within it. So let's expand this out here. FGM we know is 117.6 newtons minus the force of kinetic friction. I'm going to do that in purple over here. Just like we found static, we can also find kinetic friction. The force of kinetic friction is just equal to 0.43 our mu k times the normal force, which again is the same 68.6 newtons, because friction is only acting on M1 and M2. So the normal force is just the normal force between these two in the table. And that is equal to some number. (29.5). So our force of kinetic friction is 29.5 newtons. All right, now we can put that in over here. We know that FGM minus force of kinetic friction, we can put in 29.5 newtons equals, now again we need the combined mass of all three, so 7 plus 12 comes to a total of 19 kilograms times the total acceleration of our three-block system. So all we need to do is take 117 minus 29.5, 117.6 minus 29.5 gives us 88.1, and then we're going to divide that by 19 kilograms, giving us a total acceleration of 4.64 meters per second squared. So a total equals 4.64 meters per second squared. Now, the other thing we're asked to do is find the force of tension on mass 1. There's a couple ways we could do this. The way that I'm going to choose to do it here is to just look at mass 1 and realize that if that mass is accelerating at 4.64 meters per second squared, if we draw a free body diagram for it, the forces will have to work out such that the acceleration of that mass 1 will be 4.64 meters per second squared. So let's draw a quick free body diagram just for mass 1. So for just mass 1, of course we have gravity and normal force. You don't need to worry too much about those. Those are going to cancel out. But we also have force of tension in that rope that is pulling it in the direction of positive motion, to the right as we see it here. So this tension right here is pulling it to the left or in the direction, the right, to the right or in the direction of positive motion. And then friction is resisting that. We do know it's kinetic friction. And that kinetic friction is pushing back against it. So, in order to find the force of tension, we'll need to realize that if we do sum of forces here, and here I'm just going to call it the x direction, sum of forces in the x direction or the direction of motion is equal to force of tension, which is positive, moving in the direction of positive motion, minus the force of kinetic friction, and that must be equal to our mass m1, because again, this is a free body diagram for m1, must be equal to the mass m1 times whatever our acceleration is for the total 3-block system. So 4.64 meters per second squared. All right, we know m1 is 2 kilograms, and we know that the force of kinetic friction for this object. This is where we have to be a little careful. We can't just put in 29.5. Now, why can't we do that? Because this force of kinetic friction was based off these two objects together resting on the table. If we are just looking at mass m1, we'd have to take the force of kinetic friction only for mass m1. So in order to do that, I'm going to say that force of kinetic friction is equal to 0.43 times the normal force just for this. So that would be 2 kilograms times 9.8, or 19.6 newtons. So 19.6 newtons is the gravity and normal force just for m1, which is 2 kilograms times 9.8 meters per second squared. So the force of kinetic friction will turn out to be 8.43 newtons. So coming back over here, if we know this is 8.43 newtons, and we know that m1 has to be our 2 kilograms times 4.64 meters per second squared, then the force of tension we can find here by adding, by adding 8.43 to this total amount over here. So we're going to take 2 times 4.64.
Let me ask you a question.
Yeah.
Kids gone? They're gone for the day?
Yep, yeah, the kids are done, yep. Just making a video. Okay, so here we have 2 times 4.64, I got 9.28, and then I'm going to add 8.43 over here. And we get force of tension must be a total of 17.71 newtons. All right, so force of tension felt by mass 1, which we found here by saying it must accelerate at 4.64 meters per second squared, same as all the other objects that are in our system. So that force of tension must be 17.71 newtons in order for it to accelerate at 4.64 meters per second squared. So by drawing free body diagrams first for the whole system, all 3 objects together, and we had to be careful with our directions of motion and how we drew things, and it did get a little bit weird because we had to put positive motion, negative motion as our directions. And then we were able to look at just mass m1. Based off that acceleration, we found the total acceleration 4.64, and we were also able to find the force of tension experienced by mass m1.